previous lesson. Okay.
What was the last class you guys were talking about?
Okay, so in the previous class lesson,
You were on the English literature. Oh my god, this is like the second class.
so I'll try again. In the last lesson, we looked at the values that I got from my experiment. I explained to you that I have different uncertainties, just to refresh your memory. If you have three values after the decimal point, it means that my uncertainty will be 0.001. See, also 3. So your scales have two values that you use. So that means your uncertainty will be 0.01. Because you are subtracting the two masses from each other to get the mass of the water, it means that your uncertainty for the mass of the water is going to be 0.002. Please note that when you get the average of 5 masses, your uncertainty for the 5 masses will remain 0.002. They do not change. So for one mass, for the first trial, your uncertainty for the mass is 0.002 because you're subtracting two masses from each other, and then you have to add those two uncertainties together. If your group did not redo the mass of the water, then obviously you only do it once, because some groups redid the mass 5 times, but you didn't really have to because there was no evaporation, so your mass of your water should have remained the same. The same with temperature. I used the thermometer and my uncertainty was 0.1, and if I subtract my two values for my temperature, then my uncertainty will be 0.2. I then used this equation to determine the heat that was transferred to the water, and the answer that I got here had to be written to 3 significant figures. So I had to change this value to 3 sig figs, and this value that I get here is called my theoretical value or my theoretical yield. So in theory, this is actually my actual value. Sorry, my mistake. Let me fix this. This is the actual value. Okay, then I had to change the heat or the energy from my pasta that I burned, and to find out how much energy is in pasta according to the manufacturer. To do that, I had to consider these two conversions. That 1 calorie, this capital C calorie, is calories in food, and a small c calorie is the calorie in the heat, and this calorie is in the heat of water, heat transferred to water. So when I look at heat energy, it's a small letter calorie, and there's 1 calorie, nutritional calorie, in 1000 calories, heat calories. Also remember that 1 calorie is equal to 4.184 joules of energy. The manufacturer, as you can see when I showed you the diagram, the manufacturer says that in 56 grams of the pasta that I burned, there's 200 calories of energy. I had to go and determine, if I have 56 grams of pasta and I have 200 calories, I had to put that into joules, which I did here. And then I had to take the 56 grams of pasta and determine how much energy is in 1 gram of pasta. Because in 56 grams I have this much energy, so in 1 gram I end up having X. If I solve for X, then you notice that you end up with 14,942.86 joules of energy. You can write that as 2 significant figures because of the fact that you have 2 significant figures here, but you don't have to. You could keep that value as well. It will make it more accurate. Then we had to go and look at the mass of the spaghetti that we burned. So to get the mass of the spaghetti, I got the mass of the spaghetti, and then I had to determine my uncertainty for that as well, right? according to my calculations now, if I have 1.096 grams of spaghetti or pasta, I'm going to release by burning it, according to the calculation that we did here. This one here, according to this calculation, when you burned that spaghetti, you got 5.70 times 10 to the power 3 joules of energy, right? So if 1.9096 joules gives me this much energy, I had to convert it to 1 gram, because that's the only way I'm going to be able to compare what I did to what the manufacturer says I should get. So now when I burn 1.096 grams of pasta, I determined that 1 gram of that pasta is going to release 5.20 times 10 to the power 3 joules of energy. And this is where we stopped. This is where we finished. And the manufacturer says that 1 gram of my pasta is going to release 1.5 times 10 to the power 4 joules of energy, or as we had it more accurately here, 14,942.86 joules of energy. Do you agree with me? Okay. So there's a difference between the two. Can you see there's a big difference in value? My answer is not even close. So there's a big margin of error. I need to determine that error. And to determine that error, I'm going to take my theoretical value, I'm going to subtract from that my experimental value, and then I'm going to divide it by the theoretical, times it by 100, and that's going to put it for me into percentage. So, quickly do that for me. So,
just a question real quick. For the theoretical value for 1 gram of energy, what's the answer again? I'm saying for the theoretical value.
So 1 inside of this person.
So, as you can see here, in theory, according to the manufacturer, I should get 14,942.86 joules of energy. That's how much energy I should get out of 1 gram of pasta. But I did burn pasta, 1.9096 grams of pasta, and when I converted it to make sure it's 1 gram, I see that my actual value that I got was 5.20 times 10 to the power 3 joules of energy. So, to calculate the percentage error, you have to take the theoretical value, subtract from that the experimental value, divide it by the theoretical value, and then multiply by 100, because that's percentage. Right? Yes, Rayon.
What's called for the answer of the theoretical energy per 1 gram, should it be rounded to any significant figures, or should it be kept like that?
Yes, you can stick to significant figures.
Okay.
So at this stage, how many significant figures do you look at?
I see the least that
Oh, that's a lot. 65.
So the least is 3 significant figures.
Where do you, wait, no, that's the actual value. I'm talking about theoretical.
Theoretical is the same number.
Like when we're calculating the theoretical one.
So if you want to do the theoretical value to 3 significant figures, it's 1.49 times 10 to the power of 1, 2, 3, 4, negative, positive 4.
Oh.
I almost said negative 4. Does that answer your question now?
Yeah.
1 point, so I used 1.5, but the one is more accurate, so 1.49.
Okay, so what did you get here as an answer?
65.3.
65.1%.
0.1?
No, I got point
I got 0.3.
0.3.
I got 0.3.
So 65.3%. So the percentage error, did you use this value
I
here?
used 1.50.
So I asked you to please use this one here,
I got,
which is more accurate.
I used that one, I got 65.2.
65.2. Thank you very much for those who did listen. 65.2%. Can we work with that value? 65.1.
Yeah.
Can we double check it then? So, in order to get this answer, you took 5.20 times 10 to the power of 3. Sorry, 1.49 times 10 to the power of 4 minus 5.20 times 10 to the power of 3, and then divided by 1.49 times 10 to the power of 4.
Yeah, I got 65.1.
65.1 and not 0.2.
Yeah.
Miss, because you're using your 1.4 times 10 to the power of 4. If you use 1400, that's 1.2.
So okay. So let me rather put this into a certain language then, so that we make sure that everybody doesn't make that mistake. We have to use 3 significant figures for the theoretical value, which in this case would be 1.49 times 10 to the power of 4. And I'm going to subtract from that 5.2 times 10 to the power of 3. And then I'm going to divide it by 1.49 times 10 to the power of 4. And I'm going to multiply it by 100, and my answer will be 65.1%, which is also 3 significant figures, and that is then correct. So let's work with 65.1 so that our sig figs are correct.
If we were given like a similar example, and one of the values is like 5.2 times 10 to the power of 3, we shouldn't use the full value, like the...
We will stick to 3 significant figures as we're supposed to, yes. Okay, so now that you've determined the percentage error, let's look at the uncertainties. Now, you have to apply these uncertainties. Do you know how to apply them? So let's quickly revise the uncertainties. There's mass. So there's the mass of water, right? That's one uncertainty. What was the other uncertainties?
Temperature.
Was there another mass?
Wasn't there the mass of the spaghetti?
What is that one?
0.01.
0.00.
So I'm looking at the mass, the uncertainties that we had. We had mass of the water. We had mass of the pasta. Those are the uncertainties. And then the third one was temperature, right? And the temperature was 12.4 degrees Celsius with an uncertainty of 0.2.
Miss, why is the mass 0.002?
Because you use a good
Excuse me, can we just stop for a minute, yeah? Because we want to get the absolute uncertainty. So how do we get the absolute uncertainties from this? Now remember, I'm applying it in this equation. So in this equation, my mass is the two masses of water and pasta, and then the other one is the temperature change. So how do I determine my absolute uncertainties?
Don't you convert them into percentages?
Right. So what we do is we take the uncertainty of the mass of water, which is 0.002, and I divide it by the mass of the water, 109.979. And then I have to add it to my next uncertainty, which is the mass of the pasta. So the mass of the pasta, my uncertainty is 0.002 over the mass of the pasta, which is 1.096. And my last uncertainty is that for temperature, and that is going to be 0.2 over the temperature of 12.4. And then I will multiply that with my value for what we call my theoretical value that I'm supposed to get for the pasta, and my theoretical value was how much?
1.50 for the mass of the pasta.
For the 1 gram of pasta, what was my value that I got for burning my pasta?
1.49.
So for burning the pasta, it's 5.20 times 10 to the power 3, so the actual value.
Not the theoretical.
So I take my uncertainties and I multiply it by my actual value, which is 5.20 times 10 to the power 3 joules per gram. Now if you do this calculation, what answer do you get? How much? 93.45. What is the rule about uncertainties? How many significant figures must an uncertainty have? Do you know?
As much as the value itself.
Okay, so the rule is, when you look at the uncertainties, how many sig figs is in this uncertainty?
1.
1. How many sig figs is in this one?
1.
How many is in this one?
1.
So that means if I'm going to calculate absolute uncertainty, my value also have to be one significant figure. So for 93.45, how will I write this as one significant figure?
That's minus 90.
Wait, 9.0, no, 9 times, just 9.
You died.
No, oh, you can actually.
You will write it as 90 joules per gram. So my absolute uncertainty for the energy of the pasta that was burned is plus or minus 90 joules.
Wow.
So 90 joules higher than what I got and 90 joules lower than what I got. So that's that's what we call the absolute uncertainty. We take the uncertainty of the mass of the water that we use in the experiment. We take the uncertainty of the mass of the pasta that we burned in the experiment. The uncertainty of the temperature change, because we have to look at temperature change for this experiment. Then we multiply it by the actual energy that we calculated we got from burning the pasta. And when you do that, you're going to get your absolute uncertainty. Now this 90% this 90 joules that you have is not your percentage uncertainty. This is just your absolute uncertainty. So percentage uncertainty is your absolute uncertainty divided by your theoretical value multiplied by 100. That will be your percentage uncertainty for this experiment. So you've determined your absolute uncertainty to be plus or minus 90, right? And your theoretical value that you have for this experiment, not theoretical value, my mistake again, your actual or your experimental value, sorry, my mistake. So the experimental value that we got for this experiment is the one that we used over here, 5.20 times 10 to the power of 3 multiplied by 100 to put it into percentage. Because this will tell me what is the percentage by which my answer is actually going to be out, because percentage uncertainty will give you a better picture. You all looked at, oh wow, 90. But what is your percentage uncertainty actually?
1.73.
1.73%. And we will always show the uncertainty. Remember, this is an uncertainty. How many sig figs? 1. So if I write this as one significant figure, it will be 2%. Now what do we owe this 2% error to? What caused this 2% error?
We've lost the insulation. Because when you burn the insulation, the insulation is
So the 2% error that we have, that we calculated here, is due to our equipment. The reason we have it is the limitation, and you are in a way correct, Malak, because you said it's the insulation is not really that great. So this 2% that we calculate of percentage uncertainty is basically due to the limitation of our equipment. Okay, but now what is our percentage error?
65.1.
For the IV, I think they have to be over.
So how do I determine the percentage error?
Theoretical minus experimental over theoretical times 100.
So my percentage error is equal to my, what did you say?
Theoretical, so
Theoretical minus
actual.
Theoretical minus actual over.
And we did that already, and we found that to be 65.1. So in other words, if I look at my percentage error that's not due to equipment, it would be the balance of this percentage. So my percentage error was 65.1. So 2% of that is my uncertainty. What would the rest be? What is the rest of that percentage? Why do I?
98%.
So 2% of this 65% is equipment.
What did the 63?
The rest of it is due to what?
external factors,
Like what?
like heat,
Temperature, room
loss,
temperature.
heat is lost. Not lost, but it's not being.
Could it be human error?
Yeah.
So human error can be one reason why we had this. What else do you think could have caused this? If we look at the reasons for the error, 2% of that is for equipment. The rest of it would be poor procedure. The biggest error is poor procedure, and that's the human error part of it. Incomplete combustion In other words, the spaghetti didn't burn properly. Some of you might have burned and then you have to light it again quickly. You could have had errors in that. Also, when you had that little bit of left over in the end when you were weighing off the last piece, there could have been some black still on it. That means you are now weighing carbon, and carbon is part of the product after combustion. So smoke, all the smoke that came off in it is energy that is given off in a different form to the environment. So it's not going as heat energy into the water. The insulation was not perfect. I really tried my best. This is probably the best insulation I've ever had for this experiment. Believe me that before I got this, what we call tubes that they use for swimming, or it's actually used for insulation of glassware that comes to the lab, I had different insulation that I tried, and my percentage error was like 80%. So this insulation that we got for this experiment has greatly minimized the percentage error actually. So it's gone from an 80% error to 65, which I'm quite happy with.
Okay, so that's
But if we had the proper calorimeter, like the one that you get, that they use for burning food, then obviously you will have almost a 0% error. And then the can also absorbs some of the heat. So when you look at your questions for exams or tests, these are the type of responses that you should give as far as the
there was something like
the
this
errors.
that came on the past test. I forgot what was the question.
The 4 reasons why you didn't get the same value.
Miss,
That's
does
it.
coffee not have any calories?